Hello and welcome to today's webinar, How to Integrate a Quantum Network with Your Existing Network. Before we get started, I have a few items that I just want to highlight for you. First, if you have questions throughout today's presentation, please send us those questions directly at any time through the Ask a Question box located below. I'll be monitoring questions throughout our time together, and we'll answer as many of them as we can at the end of the presentation. You can download slides from today's presentation, as well as a quantum networking solution brief anytime by clicking on the Attachments tab below. This webinar is being recorded, and it will be available to view on demand following today's live broadcast. I'm Emily Carter. I'm the Community Manager at Aliro Quantum, and today I'm joined by Bruno Rijsman, Aliro Quantum Fellow. So welcome to the Quantum Networking live broadcast, Bruno. I'm so thrilled that you're here today to talk about the specifics of a question that we are asked all the time. How are quantum networks compatible with classical networks, and how are they integrated together? So thank you so much for joining us today to walk us through this kind of integration.
Thank you, Emily, for that kind introduction. As Emily mentioned, my name is Bruno Rijsman. I spent about 25 years of my career in technical and leadership roles at classical network equipment vendors, companies like Juniper Networks or Lucent Technologies, and I spent most of my time developing software for classical routers. About 4 years ago, through a series of coincidences, I got involved with quantum networking. And these days, I spent most of my time bringing the lessons learned from classical networking to the world of quantum networking. My personal goal is to help quantum networks evolve from science experiments to real production-grade networks. In the seminar today, I will talk about upgrading your existing classical network to a quantum network. I'll talk about why you might want to consider doing that, and I'll talk about what's actually involved in doing it. So let's begin by discussing what a quantum network is and how it differs from a classical network. We in the quantum networking community, we use the term classical network for every type of network that's not a quantum network. Pretty much every network that you've ever worked with, including the internet or the Wi-Fi network in your home, is an example of such a classical network. Classical networks send classical bits, which are just ones and zeros, and they're typically encoded as light pulses in optical fibers or as radio pulses sent through the air. Quantum networks, on the other hand, communicate using quantum bits, which are also known as qubits. These quantum bits have special properties that are described by the laws of quantum physics. One of the most famous of such properties is called superposition, which is often and slightly incorrectly described as a qubit being both a 1 and a 0 at the same time. And another famous property is called entanglement, where the fate of two qubits is connected even if they are very far apart from each other. But there's many other quantum properties that make quantum networks special. Now, in this seminar, I'm not going to get into the details of quantum physics, but the only thing that is important to remember is that these special quantum properties allow quantum networks to do certain things that are impossible or very difficult to do with classical networks. On the other side, quantum networks also have unique limitations that are very different from the limitations of classical networks. So in this seminar, my goal is to show you that classical networks and quantum networks each have their own strengths and weaknesses, and by combining quantum networks with classical networks, we can get the best of both worlds. So what are some of the things that quantum networks are good at, but that classical networks cannot do? In other words, what are the applications or the use cases for quantum networks? Back in January, we presented a seminar called Why Quantum Networks, Why Now? That describes these applications in great detail. And the link to that seminar is given at the bottom of this slide. For now, I'll just briefly summarize the main use cases for general-purpose entanglement-based quantum networks. The most well-known and most mature application of quantum networks is called quantum secure communications. We need quantum secure communications to deal with something that's called Q-Day. This term Q-Day refers to the problem that existing security protocols such as RSA or Diffie-Hellman will very likely be broken by quantum computers due to the discovery of Shor's algorithm. There are already multiple companies out there that are right now offering quantum key distribution or QKD products that use quantum networks to fix these broken protocols. In this seminar, I will use the term quantum secure communications, or QSC, in a slight more broad sense to refer to the evolution of QKD that uses entanglement and quantum repeaters. QSC builds on the good parts of QKD and addresses some of the main weaknesses of QKD. Quantum secure communications continue to use protocols such as E91 or BBM92 that have been studied for many decades and that are well understood and that have security proofs. But instead of using insecure trusted relay nodes like QKD does, quantum secure communications uses quantum repeaters. And I'll cover this distinction in more detail in a later slide. Once you build a quantum network out of quantum repeaters, it becomes a general purpose entanglement generating quantum network, and sometimes we refer to this as a universal quantum network. What this means is that you can also run other applications on the same quantum network, including, for example, clustered quantum computing, distributed quantum computing, also known as the quantum internet, and distributed quantum sensing. Now, while quantum networks enable new applications, they also have their unique limitations. Most of these limitations are caused by the fact that quantum networks use extremely weak light pulses, typically single photons. These single photons are susceptible to loss, which increases exponentially with the distance of the optical fiber. As a result, the range of a quantum network point-to-point link is limited. Now, the exact limit varies quite a bit depending on many factors. For example, what kind of source you use, or what kind of detector you use, or what kind of protocol you use. Some research systems have already achieved 800 kilometers of distance. But 100 kilometers is a more typical maximum distance for currently available commercial products, and that's the number that I will use in today's seminar. Beyond 100 kilometers, you need trusted relay nodes, quantum repeaters, or satellites. The second limitation is that the throughput of a quantum network expressed in qubits per second is much lower than the gigabits per second or even terabits per second that you might be used to from your classical network. Once again, the exact limit varies, but about 1 million usable qubits per second is typical for currently available commercial products when the links are very short. Once we extend the distance and we get closer to the limit of 100 kilometers, the throughput typically decreases down to a few thousand qubits per second. The third limitation is that the links in a quantum network must either be optical fiber connections or point-to-point free space laser connections. Those free space connections can be terrestrial or they can be satellite. Currently, radio links such as Wi-Fi networks or copper links such as DSL are not supported by quantum networks. In some ways, quantum networking is a technology that's actually quite mature. In fact, quantum networking is considered to be more mature than quantum computing, for example. There's already multiple companies that have been offering commercial QKD products for over 10 years now, and these products have already been deployed in operational networks. The components that we need for the next generation of general-purpose entanglement-based quantum networks are just now being commercialized. That includes things like quantum memories, transducers, and quantum repeaters. The range, the speed, and the cost of quantum networks will improve over time as a result of further developments into things like multimode quantum memories, quantum error correction, integrated photonics, and other technologies. One of the questions that we get asked almost every single seminar is, will quantum networks replace classical networks? And the answer is clearly no. We will never, ever watch Netflix or do a Zoom call over a quantum network. Instead, quantum networks will be used in conjunction with classical networks. We can understand this a little bit better by looking at what happened on the compute side. Classical computers have been using coprocessors to perform specialized tasks for a very long time already. We have things like graphical processing units or GPUs that are used to offload graphics rendering. We have things like tensor processing units or TPUs that are used to offload machine learning, and we have data processing units or DPUs that are used to offload networking tasks. These coprocessors do not replace general purpose CPUs. Instead, they augment the CPUs by offloading some very specific specialized tasks. Similarly, quantum processing units or QPUs will not replace classical computers either. Just like GPUs and TPUs and DPUs, the quantum processing units will be used to offload very specific tasks that quantum computers happen to be good at. And that includes things like drug discovery, material design, financial simulation, logistics optimizations, cryptanalysis, and things like that. Now, although quantum computers are much better at certain tasks than classical computers, there's plenty of tasks that quantum computers are just horrible at. No one would ever dream of using a quantum computer to edit an Excel spreadsheet or to play a video game. So quantum computers will never replace classical computers. Now, the exact same thing is true for quantum networks. Quantum networks will never replace classical networks. Instead, quantum networks will augment classical networks. There are some very specific applications that quantum networks are very good at, and that includes things like secure communications, but also connecting quantum computers to each other or connecting quantum sensors to each other. Quantum networks are not just better at these applications. Some of these applications are simply impossible with classical networks. For example, if you want to build a clustered quantum computer, you cannot use a classical network. It's only possible with a quantum network because you need to transfer quantum states in the form of qubits from one quantum computer to another quantum computer, and this is only possible with a quantum network. Now, in the rest of this seminar, I will discuss how quantum networks and classical networks integrate with each other. Here's a concrete example of how a classical network and a quantum network work together. In this slide, and in fact, in the rest of the seminar, I will focus mainly on the quantum secure communications use case because that's the most mature application for quantum networks. I could draw similar diagrams for clustered and distributed quantum computing and sensing. In this diagram, at the top in blue, we have the classical network. There are two parties that want to exchange encrypted data over this classical network. There are many companies, including companies like Cisco or Juniper or Ciano or Fortinet, that offer the hardware encryptor devices that do the encryption at various layers in the classical stack. The bulk encryption of the data can take place at multiple gigabits or even terabits per second, and they use symmetrical encryption protocols, typically the Advanced Encryption Standard, or AES. These symmetric encryption protocols need both parties to agree on a session encryption key. In today's networks, this is typically implemented using asymmetrical encryption protocols such as RSA Diffie-Hellman or elliptic curve Diffie-Hellman. These existing key establishment protocols are expected to be broken by quantum computers due to the discovery of Shor's algorithm. These broken algorithms need to be replaced by a new key establishment protocol which is safe against attack by quantum computers. And this is what we mean when we use terms like quantum secure communications or post-quantum security or post-quantum cryptography. There are multiple ways to do this, but one possible way to implement quantum secure key establishment is to use a quantum network. And in this diagram, the quantum network is shown in red at the bottom of this slide. The quantum network uses the special properties of quantum physics to enable the establishment of an encryption key between two parties in a secure manner. I'm not going to get into the nitty-gritty details of how this works, but the basic principle is that the laws of quantum physics are leveraged to make sure that any attempt to steal the key is guaranteed to be detected. And that's why often the term physics-based security is sometimes used to describe this approach. Now, there are two important things to notice about this diagram. The first observation is that the quantum network is not responsible for the high-speed bulk data encryption at multiple gigabits per second. The high-speed encryption still happens on the classical, on the blue side of this network. The quantum network, the red part, is only responsible for producing the encryption keys. The quantum network is more than fast enough to produce the necessary encryption keys, even if you roll over the keys very frequently. The quantum network hands over the encryption keys to the classical encryptor using a well-defined interface that I will discuss in much more detail a little bit later. The second observation to take away from this slide is that the quantum network does not replace the classical network. You do not need to do a forklift upgrade of your classical network. The quantum network only augments the classical network to offload one specific function, which in this case is the establishment of encryption keys. I will now discuss the integration between the classical network and the quantum network at 3 different layers. First, I'll talk about the physical layer, then the application layer, and finally, the control, orchestration, and management layer. So I'll begin with the physical layer. Devices in a quantum network are connected to each other using 3 different channels: the quantum channel, the real-time classical channel, and the non-real-time classical channel. Each of these channels can be implemented using optical fiber connections or free space point-to-point laser connections for applications like vehicles or drones or satellites. When optical fibers are used, each channel can be assigned to a separate optical fiber strand, but it's also possible to multiplex multiple of these channels into a single fiber using dense wavelength division multiplexing, or DWDM. I'll describe each of these 3 channels in more details on the next couple of slides. The first channel that I'll discuss is the quantum channel. This is the channel that carries the actual qubits, which encode the quantum information, typically in the form of individual photons. There are multiple different encoding schemes, including polarization encoding and time bin encoding, each with their own advantages and disadvantages. Typically, the quantum channel is carried over optical fibers. It's possible to use normal telco fiber that's already in the ground, and it's not necessary to deploy any new type of special fiber for the quantum channel. That said, there are some specific requirements. The main requirement is that the optical path that is used for the quantum channel is not allowed to contain any active components, such as classical routers or classical switches, or even simple classical amplifiers. The technical reason for this is known as the no-cloning theorem. It is, however, allowed to include passive components, such as patch panels or layer 1 optical cross-connects. It is also possible to carry the quantum channel over a free space connection. That free space connection may be a terrestrial point-to-point connection, or it may be a ground station to satellite free space connection. But either way, that free space connection must be implemented as a point-to-point laser. Radio networks, such as Wi-Fi networks or cellular networks, are currently not suitable for the quantum channel. The second channel is what I call the non-real-time classical channel. This channel is used to carry non-real-time control protocols, management protocols, and orchestration protocols. For management and orchestration, there's a trend towards using YANG, netconf, and restconf. Netconf and restconf are the exact same management protocols that are also used in classical networks. The network management YANG data models are in the process of being adopted to quantum networks, and I'll talk more about that in detail. The control protocols are used to control various aspects of the quantum network. A subset of those control protocols is extremely hard real-time, in the sense that they must be synchronized down to the nanosecond level. And those real-time control protocols have to be carried over a separate channel, which I will discuss on the next slide. But most of the control protocols are not of that hard real-time nature. In the context of quantum secure communications, examples of such non-real-time control protocols include things like key post-processing, specifically information reconciliation or privacy amplification, and key delivery protocols. In the more general context of general-purpose entanglement generating quantum networks, examples of such non-real-time control protocols include things like topology discovery, resource discovery, and the establishment of quantum virtual circuits. These non-real-time control protocols can be carried over the non-real-time classical channel, which is the one shown here, along with orchestration and management protocols. This non-real-time classical channel uses completely normal TCP/IP and Ethernet networks. So you can continue to use your existing classical channel, your existing classical network with routers and switches for this particular channel. The third channel is the real-time classical channel. The real-time classical channel is used to carry that small subset of control protocols that is very hard real-time in nature. As I mentioned in the previous slide, these hard real-time control protocols require extreme precise synchronization down to the nanosecond level. In the context of quantum secure communications, examples of such real-time control protocols include things like clock synchronization, polarization calibration, and key sifting. In the more general context of general-purpose entanglement-based generating quantum networks, examples of such real-time control protocols include things like elementary entanglement generation, entanglement swapping, entanglement purification, teleportation. The diagram at the bottom of this slide shows a concrete example of elementary entanglement generation. In this example, we have a source on the left and a source on the right, and they each generate photons that need to arrive at the thing in the middle, which is called the Bell state analyzer, at exactly the same time down to the nanosecond. That's why we need extremely precise clock synchronization. Also, this entanglement generation protocol is non-deterministic in the sense that multiple attempts are needed to get a successful entanglement. So we need some sort of real-time protocol to report every single photon detector click at the Bell state analyzer back to the sources so that the elementary entanglement generation attempts can be repeated until we finally get a successful entanglement. This requires an enormous volume of control messages, and they need to be very precisely timed. And for that reason, these real-time control protocols typically do not use TCP or not even Ethernet. Instead, these protocols very often use proprietary framing, and they're typically implemented in custom FPGAs. Now, because these protocols use custom framing and not standard Ethernet framing, these hard real-time control protocols have to be carried over a dedicated and separate channel, which I refer to as the real-time classical channel. But there's no standard name for it. It's also known by many other names. If you look at the documentation of some of these products, you'll see terms like the service channel or the synchronization channel. But the main point is that because of this proprietary framing, the optical path for these real-time classical channels is not allowed to contain any IP routers or Ethernet switches, because they won't recognize the proprietary framing. But you are allowed to use DWDM, muxes, or amplifiers, unlike the quantum channel. At the beginning of this seminar, I mentioned that one of the main challenges in quantum networks is the limited distance for point-to-point links. As a general rule of thumb, we can say that the maximum allowed loss on a point-to-point quantum link is about 20 decibels, which translates roughly into a distance of 100 kilometers if we assume the loss for the C-band in standard telco optical fiber. The exact distance limit depends on many technical details, for example, what sources or detectors you use. That limit of 100 kilometers may actually be higher or lower, but 100 kilometers is typical for currently available commercial products. And that's the number that I will use in my examples. That limit of 100 kilometers is not a black and white hard limit. In the blue graph at the bottom of this slide, you can see that the throughput of the quantum link actually goes down smoothly as the link distance increases. In this particular example, at around 23 decibels, which is a little bit more than 100 kilometers, the throughput drops down to essentially zero. Because of this, beyond 100 kilometers, you need some sort of relay mechanism to extend the distance of the quantum link. And that relay might be a trusted relay node, or a quantum repeater, or a quantum router, or a satellite. And we'll discuss those options a little bit later. In many real-world deployments, it's very desirable to use dense wavelength division multiplexing, or DWDM, to multiplex multiple classical channels and a quantum channel onto a single fiber. That greatly reduces the cost of the network because you have to deploy fewer fibers. It's customary to put the quantum channel in the O band and the classical channels in the C band to maximize the wavelength difference and minimize the interference between the classical and the quantum channel. Now, there's a downside to that, because if you put the quantum channel in the O band, the maximum distance is reduced by another 40% or so, because the optical fiber has more loss in the O band than in the C band. GÉANT, which is a pan-European research network in collaboration with the University of Twente in the Netherlands, published a very interesting paper studying what it would take and how much it would actually cost to upgrade their existing classical network to a quantum network. In this particular study, we are evaluating a QKD application, and for that reason, they're only considering QKD trusted relay nodes. But a similar methodology could also be used to evaluate general purpose entanglement-based quantum networks. The map shows one ring in the existing GÉANT classical network. The blue squares represent existing points of presence, or POPs, and the purple triangles represent existing classical amplifier locations. And the lines represent optical fiber spans between these POPs and amplifiers. The study considers deploying quantum relay nodes at the existing POP and amplifier locations, and that makes a lot of sense because that's where we already have buildings and we already have access to power in the management network. And then the study looked at each one of these fiber spans and color-coded them green, orange, or red. The green links have less than 20 decibels of loss in the O band, which maps to roughly less than 60 kilometers of distance. That is the ideal and cheapest scenario for a quantum link, because we're able to use wave division multiplexing to multiplex the quantum channel onto the same fiber that's already in place for the classical channels. You may have to deploy some new DWDM devices if they're not already part in the network, but we don't need to deploy any new fiber or rent any new fiber. And that's typically where the bulk of the cost is in a network. The orange links have less than 20 decibels of loss in the O band. They have more than 20 decibels of loss in the O band, but still less than 20 decibels of loss in the C band. And that translates to a distance of roughly 60 to 100 kilometers. Now, in this case, we are forced to carry the quantum channel in the C band because the O band has too much loss. And as a result, we cannot multiplex the quantum channel and the classical channel onto the same fiber, because if we did that, we would have to put both of them in the C band, and then we would get too much interference. Hence, we have to deploy or rent new fiber that is dedicated to the quantum channel. And this tends to be a lot more expensive. Finally, the red links have more than 20 decibels of loss in the C band, which translates roughly to more than 100 kilometers. And in this case, the distance is too long for a quantum channel, even if you used a separate fiber. In this case, the only option is to introduce an additional relay node, which is the most expensive scenario. So from this example, it's very clear that the maximum distance of a point-to-point quantum link is a very important factor in the overall feasibility and cost of a quantum network. Now, this particular GÉANT study is a little bit unusual in the sense that they studied a very large pan-European network, and currently most quantum networks are deployed in smaller metro region networks. By now, I've mentioned a couple of times that you need some sort of relay node once the distance of a point-to-point quantum link exceeds roughly 100 kilometers. And there are several options for implementing these relay nodes. In current generation quantum key distribution networks, so-called trusted relay nodes are used. The way that they work is that they first establish a point-to-point encryption key on each of these point-to-point links. And then the end-to-end encryption key is essentially forwarded hop by hop through this series of encrypted point-to-point links. I'm oversimplifying a little bit, but that's essentially what happens. As you can see in the top row of this slide, this has an important disadvantage. And that disadvantage is that the end-to-end key is exposed in the clear inside each of these trusted relay nodes. So the name trusted relay node is actually a little bit misleading. It's not called a trusted relay node because the node is trustworthy. It's called a trusted relay node because you have to trust that node not to leak the exposed key. This need for trusted relay nodes in QKD networks is one of the most important criticisms on the current first generation of quantum key distribution networks. A more secure, a better method is to use quantum repeaters instead of trusted relay nodes, which is shown in the second row of this slide. Quantum repeaters offer two important benefits. The first benefit is that the keys are not exposed at the quantum repeaters. The second benefit is that the quantum network, which is built out of quantum repeaters, is what we refer to as a universal general-purpose quantum network. It can be used not only for quantum secure communications, but also for other applications such as clustered and distributed quantum computing or sensing. You can think of the current first generation of QKD networks as being similar to the telephone networks of the 1980s, in the sense that they can only run one single application, namely telephony. And quantum repeater-based quantum networks are more like the internet of today in the sense that they can run multiple applications. The challenge with quantum repeaters, however, is that they're an emerging technology. The components that are needed for to build quantum repeaters, things like quantum memories, are only just now becoming commercially available. But we expect that quantum repeaters will become a viable option to replace trusted relay nodes in the next few years. Finally, for intercontinental distance, there's the option to use satellites and ground stations connected by free space lasers. Because the loss in vacuum of space is much lower than the loss in fiber, these satellite-based connections can cover very large distances up to several thousand kilometers. The downside, obviously, is that satellites and ground stations are very expensive to deploy. Now, in the Géant topology that we looked at a couple of slides ago, the topology was a ring, which is very similar to a linear topology. If you have a more graph-shaped topology, such as the one shown here, then we need relay nodes that can have more than two interfaces and that can do some sort of routing functionality. This can be achieved in several ways. If the distance is short enough, for example, in a metro network, you can use layer 1 optical switches. These optical switches can be relatively slow, such as a MEMS switch, for example, or the optical switches can be very fast, such as a Mach-Zehnder interferometry switch. And in that case, they can do very dynamic switching. If the distance gets a little bit longer and you cannot use layer 1 optical cross connects, then in the current first generation of quantum key distribution networks, it's customary to deploy multiple trusted relay nodes, essentially back-to-back, or there are also products that are trusted relay nodes with multiple ports. In this case, you need a software layer for the routing functionality and to choose the end-to-end path for the key generation. Later in the seminar, we'll see that there's actually quite a bit of standardization already happening in this area. This approach has the same problem that I mentioned before. The relay nodes need to be trusted because the key is exposed at each hop. And once again, a better approach is to use multi-port quantum repeaters, which we refer to as quantum routers. Once you have quantum routers, you have a general-purpose, general topology entanglement-generating network that can support multiple applications. Next, I'll discuss integration between the classical network and the quantum network at the application layer. Once again, I'll focus on the quantum secure communications application when I'm talking about the application layer integration. In this case, the job of the quantum network is to generate encryption keys, and the job of the classical network is to do the bulk encryption using those keys. So we need some sort of interface between the quantum network and the classical encryptors to hand off those keys. Contrary to what you might expect, this key delivery interface is actually already very well defined and standardized by ETSI, which is the European Telecommunications Standardization Institute. ETSI has defined a series of so-called group specifications that include a definition of this key delivery interface. These ETSI specifications are publicly available at no cost, and they're actually quite short and very readable, and I highly recommend that you download them and read them. The first of these group specifications is known as ETSI QKD Group Specification 004, and I'll just call it ETSI 4 for short. Before I get into the details, I'd like to point out one thing. The ETSI specifications are written using very specific QKD language. However, many of these ETSI specifications can also be applied to quantum repeater and quantum router-based networks with few or no changes. In this diagram, the yellow boxes are the classical encryptors, and the red and green boxes are the quantum networking devices. We can see the quantum channel, the non-real-time classical channel, and the real-time classical channel, which is referred to as a synchronization channel here, that we discussed a few slides ago. The actual key delivery interface that ETSI 4 describes is the vertical arrow in this diagram, which is labeled QKD application interface between the yellow and the green boxes. Now, ETSI 4 is a quite abstract document, and it's not concrete enough to actually implement multi-vendor interoperable implementations. Specification ETSI 14 takes the general principles that were described in ETSI 4 and makes them much more concrete and specific. ETSI 14 defines a REST interface, which is a very common type of HTTP-based interface. If you have a classical encryptor from one vendor and a quantum networking device from another vendor, and they both claim support for ETSI 14, then you can be quite confident that they will interoperate with each other. In fact, most of the existing QKD vendors already support ETSI 14, and several classical encryptor vendors are in the process of adding ETSI 14 support to their products. The ETSI 14 protocol is actually extremely simple. There are only 3 messages. The first message is the get status message, which is used to check whether a quantum networking device has keys available and other operational status parameters. The classical encryptor on one side of the network uses the get key message to request an encryption key from the quantum network. And the classical encryptor on the other side of the network uses a similar message, which is called get key with key IDs, to get the same encryption key from the quantum network. ETSI 14 assumes that the classical encryptors use some sort of out-of-band mechanism to transfer an ID for every key. And this key ID is exchanged over a classical channel, and the key ID is allowed to be public. The IETF, which is the Internet Engineering Task Force, is already working on enhancing protocols such as IPsec to facilitate this key ID transfer between the classical encryptors. Here's a concrete example of what an ETSI 14 protocol message looks like in real life. On the left, we have several examples of the get key message, which is the message that the classical encryptor uses to request an encryption key from the quantum network. In its simplest form, the encryptor simply specifies the number of requested keys and the size of each requested key. And then on the right, you can see an example get key reply message. This is the message that the quantum network sends back to the encryptor to actually provide the requested encryption key. Each provided key has a key ID and the actual key value itself. Now, this REST protocol between the encryptor and the quantum network is, of course, itself encrypted and mutually authenticated. Just like any other network, quantum networks need to be controlled, managed, and orchestrated. This is another area where quantum networks and classical networks are deeply intertwined with each other. There has been a surprising amount of standardization in the area of controlling, managing, and orchestrating quantum networks. The ITU-T, which is the International Telecommunications Standardization Institute, has published a series of standards which is called the Y3800 series, and which describes quantum networks. These ITU-T standards are also publicly available at no cost, although they're a lot more dense and more difficult to read. Just like the ETSI specification that we discussed earlier, the ITU-T standards are currently framed in terms of QKD networks. But many of these standards could easily be generalized to quantum repeater-based networks and other types of applications, such as distributed quantum computing. The left half of this slide is taken from ITU-T Y3803. It shows the various layers in a quantum secure communications network. At the bottom layer, we have the actual quantum networking devices. The layer above that shows the quantum key management, the key management layer. And above that, we have the quantum network controller, which is the yellow, small yellow box. This controller is similar to a software-defined networking or SDN controller in existing classical networks. The job of the controller is to control the quantum network nodes to create end-to-end quantum sessions, in this case for the delivery of encryption keys to the application nodes. In today's QKD networks, these quantum relay nodes are assumed to be trusted relay nodes, but the same approach of using a controller and setting up sessions also works when we're creating end-to-end entanglement generation sessions in a quantum repeater-based network. The application nodes are shown in the service layer at the very top. In this concrete example, they are classical encryptors. But if we generalize these IDs to entanglement-generating quantum networks, these application nodes could also be things like quantum computers in a distributed quantum computing application. The two white boxes, which are sitting right next to those layers, are the management functions. There's one management function responsible for managing the devices in the quantum network, and there's also an orchestration function, which is responsible for managing the end user services. The figure on the right half of this slide is taken from ITU-T Y3804. It shows the responsibilities of each of the functional blocks that I just discussed and the interfaces between them. Now, time doesn't permit me to discuss all of these little boxes in detail, but I'm showing this diagram anyway to make the point that all of these blocks and all of these interfaces between them have in fact already been standardized. As of now, ITU-T has not yet standardized any concrete protocols. They've only defined abstract reference models, such as the ones that I just showed you. And once again, ETSI has gone further. They have defined actual concrete protocols for controlling, managing, and orchestrating your quantum network. In particular, ETSI Group Specification 15 defines the protocol between the quantum network controller and the quantum nodes. In this diagram, the yellow box is the quantum network controller and the blue boxes are the quantum networking nodes. One of the blue boxes has been blown up on the left to show its internal structure. ETSI 15 defines the quantum network protocol using Yang data models and using the netconf and restconf protocols. Now, if these acronyms don't mean anything, the important thing to remember is that Yang and netconf and restconf are the exact same protocols that are already widely being used in classical networks today. ETSI 15 is an important building block for supporting multi-vendor quantum networks that contain quantum nodes from multiple different vendors. ETSI 15 includes the actual Yang data model, which describes the configuration and operational objects for quantum nodes. The Yang data model is remarkably easy to read, even if you've never seen a Yang data model in your life before. So once again, I would encourage you to download it and try to read it. For now, I'll just give you a flavor of what sorts of objects are defined in this standard Yang data model. You can configure and monitor node attributes. For example, you can retrieve the hardware and software version that's running on a particular node. You can also discover the capabilities of nodes. For example, you can discover whether a particular node can or cannot act as a trusted relay node. You can configure and monitor application endpoints. So for example, you can configure which encryptor is used to get keys from which particular quantum computing node, quantum networking node. And you can configure and monitor key generation sessions that each node participates in. These key generation sessions are very confusingly referred to as links in the specification. These links can include trusted relay nodes using a concept that's referred to as virtual links in this specification. This Yang data model even allows you to configure quality of service parameters for the key generation sessions, such as rate and jitter. That same ETSI specification number 15 also documents multiple sequence diagrams describing various workflows. There are multiple of these diagrams in the specification, and this is just one example of them. In this particular example, we show two application nodes, meaning two classical encryptors, registering themselves with a quantum network and establishing a key exchange session amongst themselves. The final ETSI specification that I will discuss today is ETSI 18, which defines the interface between the orchestrator and the controller. The gray box at the top is the orchestrator, which is responsible for orchestrating end-to-end services for end users. In this case, the end-to-end services that are being orchestrated are the delivery of encryption keys. For example, an end user could ask for a key delivery session between, say, Amsterdam and Brussels with a key rate of 5 kilobits per second of key material per second. And it's the job of this orchestrator to make this happen across multiple management domains. In this slide, there are two management domains. There's the quantum network management domain on the left and the optical transport network management domain on the right. In the quantum network domain, the orchestrator has configured the quantum nodes to produce and relay quantum keys. And to do this, the orchestrator talks to the quantum network controller that we discussed in the previous slide. And this is the blue box at the top of the left side. On the optical transport network, or the OTN side of this picture, which is the right half, the orchestrator is responsible for configuring the optical transport nodes to create the necessary optical paths in the network. And for this, the orchestrator talks to the OTN controller, which is the yellow box at the top of the right half of this diagram. ETSI specification 18 defines the interface between the orchestrator and the quantum networking controller, which is the red line in this diagram. Once again, the ETSI specification is not some abstract reference model. It's an actual protocol that can be implemented by real products, and it's specified using a Yang data model. So this brings me almost to the end of this seminar. So far, I've discussed what a quantum network is, how it differs from a classical network, and how quantum and classical networks can work together. I've discussed several interfaces and protocols and standards, mainly in the context of quantum secure communications. And in my view, the next step is to generalize all these interfaces and protocols and standards that are being developed beyond QKD to general purpose entanglement-based quantum networks. So what's involved in that? At the physical layer, we need to go beyond trusted relay nodes and introduce quantum repeaters and quantum routers. At the control layer, we need to introduce entanglement generation protocols, including elementary entanglement generation, swapping, purification, and teleportation. And at the management and orchestration layer, we need to enable new end-to-end services beyond just key generation and enable new applications such as clustered and distributed quantum computing and sensing, and also an application which we refer to as quantum testbed as a service. And finally, the application delivery interface that I talked about when I talked about ETSI 14 needs to support the delivery of entanglement beyond the delivery of keys. So I'd like to thank everyone for their attendance. If there's any questions, I'd be happy to answer them here today, and we're always available offline as well.
Bruno, thank you so much for this very clear and thorough discussion of integrating quantum networks and classical networks. And we do have some questions for you. So folks, if you have a question, please add it to the queue, because if there are any questions that we can't get to today, then we can follow up with you individually after our session today. First up, Bruno, clarifying question. Are you referring to BB84 or Eckert 91 type QKD? And in that case, can you talk about possibilities of side channel attacks, please?
Yes. When we talk about general purpose entanglement-based quantum networks, we're referring to a subset of QKD protocols that are based specifically on entanglement. Most of the existing QKD products are based on prepare and measure protocols. and that includes BB84, which was mentioned. There are other key distribution protocols that are based on entanglement, and this includes E91 and BB92. And those subset of key distribution protocols that are based on entanglement are the ones that are suitable for using repeater-based networks. As long as we have any kind of network that can deliver entanglement, even if it's multi-hop with quantum repeaters, quantum routers, we can use that class of key distribution protocols. In terms of side channel attacks, some of these protocols are similar in some senses to what is known as MDI protocols, or measurement device independent protocols. And those protocols have the particular property that the nodes where the receivers are not susceptible to side channel attacks. Those nodes can be what's referred to as untrusted, which sounds bad, but it's a good thing because you don't need to trust them. And so they have those particular properties greatly reduce the susceptibility to side channel attacks.
Excellent. Thank you so much, Bruno. We have another question asking about the classical side of things. So does the classical network need to meet specific requirements to be usable for a quantum network?
Well, as always, the answer is it depends. Yes and no. If we focus on the quantum secure communications use case, let me focus on the quantum secure communications use case because that's the most likely short-term production application. In that case, your existing classical network is still responsible for the bulk encryption of data using AES or some similar protocol. So you don't need to do any type of forklift upgrade of your classical network. You can continue to use your existing encryptors, your existing fiber infrastructure, your existing routers, your existing switches. Now, ideally, your encryptors support ETSI-14, and many vendors are already implementing that. But if not, you have to write some glue software that extracts the key from the quantum side of the network and injects them into your encryptors using CLI or netconf or something similar. On the quantum side, there are a few specific requirements for the classical network, which I discussed in the beginning of the seminar. And the most important requirements, well, first of all, you can continue to use normal telco fiber that's already in ground, but there are new distance limitations. And there are also some limitations on what types of components can be present in those links. For example, the real-time classical channel cannot contain any IP routers because it uses proprietary framing. So in summary, there are a few special requirements for the quantum channel and the real-time classical channel, but for the most part, you can continue to use your existing classical network exactly as is without any new requirements or without any forklift upgrades.
It's good news for all of us, actually. This next question is asking if you could be, can you be more specific for very stringent synchronization requirements down to the nanosecond? So can you give us a little more to go on there?
Sure. There are a few places where specific events need to, in the quantum channel, need to be very specific, very precisely timed. So one example that I gave in one of the earlier slides is that two nodes each generate a photon and they travel on optical fiber towards a device in the middle, which is called a Bell state analyzer. And they need to interfere with each other. And that's it's a quantum process that only happens if the photons arrive exactly at the same time so that the light pulses overlap exactly with each other when they arrive at that station. Now, how big a light pulse is depends on its bandwidth, but typically a pulse of a photon is about 1 nanosecond wide. If they arrive at exactly the same nanosecond or a few hundred picoseconds, then this effect that we need, this interference, happens. If one photon arrives a little bit too early or one arrives a little bit too late, then the quantum effect that we need to make the quantum network work doesn't happen. And so the clocks at each of the nodes that sent the original photon must run very precisely and must be very exactly synchronized so that those photons arrive at the desired time. There's other examples that I can give, but that's a typical example of why it's needed. And 1 nanosecond is a typical number. It's not as always, it's not a hard and black and white number. If it gets a little bit longer than that, the quality of the entanglements that are generated just get worse and worse. And once you get to a few nanoseconds, it becomes almost useless.
Thank you, Bruno. We have another question here asking about protocols specifically. So how do you anticipate the classical networking protocols to aid in establishment of end-to-end quantum networking connections?
Okay, so this time I'll talk about general purpose entanglement-based quantum networking and not just key distribution. There are some protocols that are very unique to quantum networking and that are completely different from classical networking. And this includes things like elementary entanglement generation, swapping, purification, and teleportation. For those things, we'll just have to invent completely new protocols completely from the ground up, and they will look very different from the protocols that we're used to. They will be very much more stateful. But once you go up the stack to the higher layers, there's a lot of things that we can reuse from classical networks. For example, when we compute the optimal path for a quantum virtual circuit, we can use a lot of the things that have already been invented for routing protocols in the classical world. We can look for the shortest path, or we can do more advanced protocols that are used, for example, in protocols like PCEP, which is the Path Computation Element Protocol, to compute more sophisticated paths. And particularly at the network management layer, there's almost nothing that is unique about quantum networks. As I showed in these slides, we can use existing protocols like Yang and NetConf and RESTConf to manage quantum networks. There's nothing we need to reinvent except the data models to describe the unique aspects of these networks.
Excellent. And our next question is going in a little bit of a different direction. You mentioned that general purpose entanglement-based quantum networks are also useful for clustered quantum computing. And how would that work if the quantum, excuse me, I'm getting tongue-tied. How would that work if the quantum network comes from one vendor and the quantum computer comes from a different vendor?
Okay, that's an interesting question. In an ideal world, you would like to be able to connect a quantum computer from one vendor to a quantum computer from another vendor using a quantum network that's produced by yet another third vendor. And personally, I very much believe that this will eventually happen, but it will take time. So at the physical layer, this will require things like standardizing the encoding scheme for qubits. For example, what frequency you use for the photons, what the bandwidth is, what encoding scheme you use, whether it's polarization encoding or time bin encoding. So that all has to be standardized at the physical layer. Then at the control layer, you have to define a whole bunch of control plane protocols, specifically the ones that I just mentioned earlier, the elementary entanglement generation, swapping, purification, etc. And then at the application layer, you have to go further. You have to go beyond networking, because we'll also have to figure out how we can enhance existing quantum computer programming languages and compilers to implement a distributed algorithm that can use the network. We have to invent the quantum equivalent of sockets. Now, in that area, there's actually quite a bit of interesting work that has already started. If you look, for example, at the NetChasm extensions to the Chasm programming language, which have been defined by QTech in the Netherlands, you'll see some early direction of work going in that direction. Now, getting to multi-vendor quantum networks is quite ambitious. Right now, we're just trying to build single-vendor quantum networks, but You have to keep in mind that in classical networking, the exact same thing happened. If you go back to the 50s and 60s, all classical networks used to be single vendor. Digital had DECnet, IBM had SNA, Apple had AppleTalk. Pretty much every computer vendor in those days had its own proprietary networking protocol. And these days, because of the need for interoperability, everything has been standardized. And the TCP/IP stack makes multi-vendor networking completely routine these days. So I have no doubt that a similar thing will happen for quantum networking. And in fact, this is one of the things that we're working on, but it will take some time before we get to multi-vendor quantum computing, clustered quantum computers.
Excellent. Sounds like we have a little bit of a roadmap from the classical internet to use in this emergent technology of quantum networking. As it develops, we kind of have an idea of where we need to go next. Bruno, we are out of time today. I'm sure that we could spend so much more time discussing with you the ins and outs of integrating these networks, but our time is up. And so anyone who had questions today that we didn't get to live, or if you have questions while you're watching on the on-demand replay, you can direct those questions to info@aliroquantum.com. Or for those of you who asked questions that we didn't get to today, we'll reach out to you directly and follow up with an answer to your question. Thank you everyone for attending our broadcast today. And Bruno, thank you so much for leading us through a really detailed breakdown of integrating quantum networks with classical networks. Thank you so much.
You're welcome.